Great. So our next speaker is J.B. Manchak, who is Professor of Logic and Philosophy of Science here at UC Irvine. J.B.?
All right. Thanks, everybody. I'm really happy to be here. The title of my talk today is a hierarchy of spacetime symmetries, fools for Heraclitus. Most of the talk is going to be coming from a paper I wrote with Thomas on this, but really this is a larger project that I've been working on with other folks too, including Hans and Jim. And yeah, I owe all three of these people a lot. They've pulled me into this new thing for me. I haven't been working in this area before, and it's so nice to have a few symmetry buddies around. You should see the text message chain I have with Thomas just every day, just math. I need a different phone keyboard or something. But it's wonderful. I've never been in a community like this where I'm talking about work together with other people in this way ever, and I'm really having a great time. So let me get started. In the second chapter of his book World Enough in Spacetime, John Irvine constructs an elegant hierarchy of classical spacetime theories. Really a wonderful chapter. I think in many ways the best chapter of the book. So clear. The hierarchy keeps track of geometric structures involved, as well as the associated spacetime symmetries. And he finds that as the spacetime structure becomes richer, the symmetries become narrower and the list of absolute quantities increases. More and more questions about motion become meaningful. Now, following Irvine, I'm going to present a hierarchy of spacetime symmetries today. But instead of comparing the symmetry properties of different spacetime theories, what I'm going to do is I'm going to restrict attention to one theory, general relativity, and I'm going to explore the symmetry properties of different spacetime models within that theory. So in this respect, the hierarchy is going to be analogous to the hierarchy of causal conditions that has long been used in the foundations of general relativity. And I'm going to highlight a few key ways in which this analogy is strong towards the end of the talk today. So there are many levels of the hierarchy. I am going to focus on just four today. I've picked these four as sort of four of the most important as I see them. So here they are. And this diagram will become more clear as we go along today. As you move up the hierarchy, the conditions require more and more structure, less and less symmetry. So each one of these four levels of the hierarchy correspond to a recent paper that I've been working on. I started work with Hans on a paper about the whole argument, and that got me pulled in. And then I started talking with Jim and Thomas about giraffe spacetimes, and we published a paper on that. And then Thomas and I started working on this Heraclitus stuff, and I'll be giving some of that today. Thomas will follow up. So there's a sense in which our talks are extremely connected. And then I have some solo work that I just started that I want to gesture to as well. Finally, along the way, I'm going to try to keep track of a number of open questions. I think there's a lot of work to do, and I'm going to try to point to questions that we could potentially resolve. Okay. So before we get to the four levels of the hierarchy, I want to start with some basics. I think it's really important to have a really good understanding of just a few key definitions. These definitions, I've noticed in the community, there's some confusion about them. And so I want to briefly review. So we start with just a definition of a spacetime. This is pretty standard. A pair mg where m is a manifold and g is a Lorentzian metric on m. I'm requiring all the usual stuff, so the manifold M has to be Hausdorff, it's connected, and so on. And now, this is the main definition that I'm going to be using throughout my talk today. Spacetimes Mg and M prime G prime are isometric if there is a diffeomorphism from M to M prime, such that when you pull back G prime to M, it just is G. And I have one more definition to set the stage, and this is a definition of a symmetry. So a global symmetry of a spacetime is an isometry from the spacetime to itself. So one can consider other definitions of symmetries. This is the one that I'm focusing on today, but it's also, it's the one that pops up in classic texts, like you find this in the appendix in Wald's book. This is the definition that Irvine uses when he's doing his second chapter in World and Upton Spacetime. It's all over both the physics literature and the philosophy literature. I'm going to stick with this one. Okay, so under this definition, symmetries of Minkowski spacetime would include translations, rotations, and boosts. Now what I want to do is consider an influential construction used in discussions of the whole argument. So let Mg be a spacetime, and let H and its complement both have non-empty interiors. There is a whole diffeomorphism from M to itself, which is non-trivial in the whole H. It's not the identity map in that region, but H does act as the identity map outside of H, outside the whole. So certainly, given any spacetime, one has all sorts of these types of diffeomorphisms that one could set up. So, given the definitions we've covered so far, it's immediate. This is an immediate proposition. It says, let Mg be a spacetime and let psi be any whole diffeomorphism you like. Then the spacetimes Mg and M where you push forward the metric, these spacetimes have to be isometric. So this is the obligatory picture to show a whole diffeomorphism. On the left we have a spacetime, say Minkowski spacetime, and we have a hole, and the diffeomorphism messes around with things in a smooth manner inside the hole. Outside the hole, we just map every point to itself. And so this counts as an isometry from the spacetime Mg to M where we push forward G. All right, so I think everyone hopefully is nodding their heads saying, yes, I got this. All right. So there's a quiz at the end of Irvine's second chapter. It's a beautiful quiz. If you haven't taken this quiz, I invite you to take it. It's a little bit trickier than maybe you might imagine. Today I have my own quiz, and it's based on what we just learned over the past 5 minutes. So I taught a little lesson, and now it's your turn, right? So the quiz is, a whole diffeomorphism is blank, a spacetime symmetry. Is it always a spacetime symmetry? Is it sometimes a spacetime symmetry? Is it never a space-time symmetry? Okay, so those are your options. This is a silent quiz. You can just think about this yourself, but hopefully you're drawn to an answer here. You've got this answer. Now, this is kind of like the Monty Hall problem, because you now have a chance to change your answer.
Is there a goat?
I'm not gonna show any goats. What I am gonna do is, well, I'm gonna show a type of a goat, I guess. So here's something to think about. I'm gonna introduce now to you a line of reasoning. It's in the air. It's in the air. I've heard this line of reasoning so many times over the course of the last few years as I've been thinking about this. Hans knows I've been on so many email chains. So anyway, here's a line of reasoning. Something to think about. This may or may not have been taken from a referee report. Consider Minkowski spacetime. Consider Minkowski spacetime. Since the metric G is the same at every point, what does that mean? Well, any point can be isometrically mapped into any other point. So every point's the same. So we know that the whole diffeomorphism will be an isometry and therefore a space-time symmetry. So if you've got a whole diffeomorphism being a space-time symmetry on Minkowski spacetime, then you know the answer is either A or B. It can't be C, never, right? So this is your chance to think about this little argument and see if you want to change your answer to B or A or B. Hopefully you did not change your answer. The answer is C. It is never. Whole diffeomorphism is never a space-time symmetry. So for some folks, I don't know, something about the words in that sentence and the way they're put together, they want to, I don't know. I don't fully understand it, but I want to talk about that for a little bit before we get to the hierarchy, just to kind of, as a type of therapy, you know? Just so we're all on the same page. So here's a proposition that Hans and I have in our paper. A whole diffeomorphism is never a space-time symmetry. This follows from a much more general uniqueness result due to Garrosh, 1969. This is his limits of space-time paper. So here's Bob's result. Let MG and M prime G prime be spacetimes, and let V and V prime be orthonormal tetrads at the points P and P prime respectively. There is at most one isometry from M to M prime, which takes P into P prime and V into V prime. There may not be an isometry, but if there is, there's only one. Okay? So given that result, the proof that a whole diffeomorphism is never a space-time symmetry goes as follows. Let MG be a space-time and let psi be a whole diffeomorphism. Let P be any point in the open region around the hole. Outside the hole. So this is the region where the diffeomorphism is acting as the identity. And let V be any orthonormal tetrad at P. Since psi acts as the identity in this open region around P, we know that psi takes P into itself, obviously. We also know that psi takes V into itself. So by the Garrosh theorem, there can be only most at one isometry that takes P into itself and V into itself. But the identity map does that. And the identity map is surely, if anything is true, the identity map is an isometry. Therefore, whole diffeomorphism cannot be an isometry, and so it cannot be a space-time symmetry. Okay? All right, so that's a proof, and perhaps that convinced you. I've noticed it doesn't always convince people, even a proof. So here's another go at this idea. Here's a concrete example of a whole diffeomorphism. It's kind of in response to that line of thought that concerning Minkowski spacetime earlier. Let's do a whole diffeomorphism on Minkowski spacetime. Let's work out all the details and see how it works out. I think it's a little bit interesting that an example of a whole diffeomorphism never appears in the original Irvine-Norton paper, nor does it appear in the subsequent literature anywhere. All of the talk is on this level. It's just like, we suppose a whole diffeomorphism exists, and then they start talking about it. Let's really understand what's going on. I think it's important, at least once in one's life, to work through the details of a whole diffeomorphism. Okay, so let Mg be a Minkowski spacetime. We'll just make it as simple as possible. 2 dimensions. We'll work in standard Tx coordinates. So M is just R2, and G is just this beautiful Minkowskian metric. Now let psi be a particular whole diffeomorphism that I'm going to define by letting psi act as the identity for all t less than or equal to 0. Then for t greater than 0, what I'm going to do is I'm going to introduce a little bump function here, which smoothly starts to shift points up away from the t equals 0 line, right? So hopefully the idea is clear. I didn't have time to work out a picture for this one, but hopefully the idea is clear. This is an honest-to-God whole diffeomorphism. And so now let's just pull back the metric using this whole diffeomorphism. So consider the non-trivial region. The first step is you're going to want to pull back your coordinate maps. So we do that here. Then we want to pull back the coordinate differentials. We use this fact to show that middle line. And then once we have that, we use that to pull back the metric itself. And this is what we find. When we pull back the metric, we have this term here in front of the dt squared, which is not 1. It's just not 1. And it's nowhere is it 1 in the t greater than 0 range. So the metric is everywhere different. This pulled back metric G is everywhere different from G. Right? So the whole diffeomorphism is not an isometry from M to itself, and so it's not a spacetime symmetry. Okay, therapy's over. All right. Hopefully it's clear. But now let's start talking about levels of symmetry. We'll start at the bottom and work our way up. So the weakest condition in the symmetry hierarchy draws on the whole construction just considered. So the condition essentially requires that when the global symmetries of a spacetime are fixed in an open region, however small, well, they're fixed everywhere. And following Garrosh, we're going to refer to these spacetimes as rigid to avoid confusion with issues related to the whole argument. So I don't want to talk about the whole argument today. If I get questions about the whole argument today, they're going right to Hans. Get ready, Hans. Okay, so definition. A spacetime Mg is rigid if for any open set O and any isometry from M to M, if psi is the identity map on O, well, then it's the identity map on all of M. If you fix the symmetries in a small open region, you fix them everywhere. And so we show that any spacetime is rigid. But I think it's worth appreciating that even though every standard spacetime is rigid, this condition can be violated in other spacetime theories. And so it's worth going through at least one example of this to see what it would be like to have a spacetime theory that wasn't rigid. Because then I think a certain type of indeterminism does appear that is not there in standard general relativity. So just consider Minkowski spacetime with two origins. So this is a non-Hausdorff manifold. And consider a map which maps every point into itself except for the two witness points. Then you want to do an exchange there. Now that map, you can work out the details, but it does count as an isometry. And so we have a situation where we can fix a big chunk of the spacetime. We can fix the symmetries there as the identity map, and yet that doesn't fix what goes on, say, in a hole that's around those witness points. So it's not the case that fixing the symmetries in an open set fixes them everywhere. And so there's a sense in which these spacetimes have a type of symmetry holes, or a type of symmetry indeterminism. Okay, so that's the bottom level. Now let's bump up a level, a stronger condition. So this is a condition that will require less symmetries, a little bit more structure. So here we're going to require that global symmetries of a spacetime just come prepackaged, already fixed. You don't have to fix them in a little open set to fix them everywhere. They already are fixed everywhere. So definition, spacetime MG is giraffe if the identity map is the only isometry. Okay. So these have various names. We chose the name giraffe because over many years with conversations with David Malamunt, he suggested one nice way to construct a giraffe spacetime. Just take Minkowski spacetime, it's got loads of symmetries, of course, but remove a compact set that is shaped like a giraffe from the manifold. The resulting structure is going to be a giraffe spacetime. So here's the picture. And you have a feel for this, right? I mean, you had translations before, you had rotation. Now, all of that is blocked by this giraffe. Here's another giraffe spacetime. This one's a little bit easier to work with. This is two-dimensional Minkowski spacetime, where this is the origin, say on a manifold R2. What I've done is I've considered this triangle region, and then I've deleted everything outside of this triangle. And the result is, hopefully, again, it's intuitive that you're not going to be able to do any rotations, translations, boosts here. That's going to be blocked by the fact that you have to map this triangle onto itself. All right. So of course it's trivial that any giraffe spacetime is rigid. Spacetime is rigid. And of course some rigid spacetimes are not giraffe. Minkowski spacetime is one. Now, I want to emphasize that virtually all example spacetimes found in the literature are not giraffe. Okay, so open any GR textbook, open any philosophy textbook which is talking about GR. Look at the examples that they're using. I'll bet you it's not giraffe. They have loads of symmetries. They have loads of symmetries, and the symmetries allow for a kind of easy presentation. So this is going to go for Minkowski spacetime. It's going to go for Schwarzschild. It's going to go for any Robertson-Walker model you're looking at. Gödel spacetime, weird spacetimes like, Taub-Nut, whatever. They all fail to be giraffe. You might get the picture that maybe giraffe spacetimes, maybe it's important to think about them. But I mean, really, our thoughts are directed at these other models. And yet, it's been claimed that everybody knows, at least everyone who thinks they know something about this, everyone knows that giraffe spacetimes are generic in some sense. So in the space of all spacetimes, giraffe spacetimes are almost everywhere, but of course, they're not generic among textbooks. There are some partial results concerning the genericity of giraffe spacetimes. Compact spacetimes is one area that's been looked at, but a general proof remains elusive. Okay, now for the third level, Heraclitus spacetimes. So the next condition in the symmetry hierarchy requires that local symmetries of a spacetime be completely fixed. So giraffe spacetimes, these are spacetimes which have completely fixed global symmetries. Now we're working with local symmetries, and we're saying, well, is it possible to fix those as well? And Thomas and I thought a lot about this question. Here's a definition that we came up with. A spacetime MG is Heraclitus if for any distinct points, P and Q, in the spacetime, and any little open regions around P and Q, there's no isometry that takes P into Q, right? So since any neighborhoods of distinct points fail to be isometric, well, there's a sense in which each event is completely unlike any other. Each event has its own geometry associated with it, which is different from the geometry at any other point. And so in such a spacetime, you might say that it's impossible to step into the same river twice. Okay, certainly any Heraclitus spacetime is giraffe. Any global symmetry counts as a local symmetry, but not the other way around. So this proposition is easy. And the other direction doesn't hold. Some giraffe spacetimes are not Heraclitus. So just take this guy. You give me any two distinct points in this spacetime, here and here, say, there's going to be an isometry, a local isometry from one point to the other. So it's almost maximally not Heraclitus. It's like all you can do is just step into the same river, just again and again and again. All right. So Heraclitus spacetimes exist. This took us a while to wrap our heads around. The example is not that hard, though. It's a very simple example. It just took a little bit of doing some calculations and putting the pieces together. But I thought it would be good to kind of give you a sense of this spacetime and what it's like. So I'm going to sketch what a Heraclitus spacetime looks like. So let's start with a portion of Minkowski spacetime in standard TX coordinates, and let's call it MG. And this is the portion I'm thinking of. The giraffe spacetime from before. This is going to be kind of like our base, and we're gonna tweak this guy a little bit. But yeah, this is where we're starting. And just to remind folks, the origin is down here at this corner. The origin is not part of the spacetime since this is a manifold. But now what we want to do is introduce a scalar field on M and let this be the Euclidean distance from the origin, so that bottom point. Then I want to define a scalar field omega just as 1 over that Euclidean distance. So omega is going to blow up as we approach that origin. And now I want to consider this spacetime here where I've taken the giraffe spacetime, portion of Minkowski spacetime, and I've just multiplied the metric by omega squared to construct this conformally flat model. So how do we know it's Heraclitus? Well, here's the little argument for that. The first step is to do a computation. You want to show that the Ricci scalar can be expressed like this. So it's proportional to the Minkowskian distance from the origin. Not the Euclidean distance, but the Minkowskian distance. And so, of course, we know that if we were to map any point into any other point, we're going to have to preserve the value of the Ricci scalar. So, what this means is that any local isometry is going to have to map a given point into another point with the same R value, which is this constant distance from the origin down here. So we've got to map this point somewhere along the blue line. We have a constraint. Okay, so now we do a similar thing, but we do it with a different scalar field, a different invariant curvature scalar field. We define this new guy, I'm going to call it Q, and we define it like this. We're going to take the covariant derivative of R twice and use the inverse metric to form a scalar field. And then when you work out the details, you can show that this Q comes out as this. So it's proportional to both R and F. So it's proportional to both R and the Euclidean distance from the origin. And so it follows that any local isometry must map a point P to a point Q with the same Euclidean distance from the origin. And what that means is that if I'm sitting here at this point P, I've got these red points are spots where I can go. So I have the second constraint. And now, of course, all I do is I just put these two constraints together, and we see that if I'm looking at a point like this, there's only one place to map it, and that's into itself. So that's a Heraclitus spacetime. Immediately, I have a couple of questions. Number one, are there four-dimensional Heraclitus spacetimes? I would love to come up with an example of a four-dimensional version of this idea. Presumably, these are around. Presumably, you'd have to come up, at least if you're following this proof strategy, you'd have to come up with four scalar fields, kind of play them off of each other. But things get pretty hairy pretty fast. And then my second question is, are Heraclitus spacetimes generic in some sense? So the community seemed to think that giraffe spacetimes were, generic. Almost everyone knows that fact, and we have some partial results. Is the situation similar with local symmetries? I don't know. My intuition seems to think that, yeah, these ought to be generic, but when I want to kind of pin that intuition down into something concrete, I fail. I've talked about this question with a few people, David, Thomas, Sam Fletcher. We've yet to come up with anything. Okay, so now let me just sketch one property or one nice thing that you might be able to prove given how structured these spacetimes are. So much to work with now at this level of the hierarchy that we can prove some pretty strong uniqueness results. So here's just one. There are others. Let's start with a definition of local isometry. So I'm going to say that spacetimes mg and m prime g prime are locally isometric if each point P has a neighborhood that is isometric with some open set in the other spacetime, and then vice versa. So, for example, any pair of flat spacetimes will be locally isometric, even though globally they can have a very different kind of structure. So they need not be isometric, but flat spacetimes, just by this definition, are locally isometric. And then we can use that definition to define what a local spacetime property is. Again, well, there are a few different definitions of what a local spacetime property is. I'm writing a paper with some folks in Budapest about this, but this is one that I've found to be useful. A property of spacetime is local if you give me any pair of locally isometric spacetimes, if it follows that one has the property if and only if the other has the property as well. So with that in place, then we can show a couple of things. Heraclitus spacetimes are locally isometric if and only if they are isometric. So that's pretty crazy. It's pretty crazy. Essentially, you've got all these little puzzle pieces, these like, you can think of little neighborhoods around points as like little puzzle pieces. And if I give you a bag of those puzzle pieces, usually there's so many different ways to put those pieces together. Like if all my puzzle pieces are flat, you can go crazy with that project. But here, the puzzle pieces are so asymmetric, so weird, that there's only one way to do it. All right, and a corollary here is that you give me any collection of local properties, there's going to be at most one Heraclitus spacetime with those local properties. So you could describe the situation as, for Heraclitus spacetimes at least, local structure determines global structure. Now, there's a great deal more to say about Heraclitus spacetimes. They seem to shed light on the relationship between symmetry, structure, and coordinates. Yeah, but for that, you're going to have to wait maybe a half hour, and then Thomas will come on the scene, and he'll talk about that. All right, so now let's talk about the final level. I call these maximally structured spacetimes. And this condition requires that spacetime have maximal curvature structure. So for any manifold M, let S of M be the collection of smooth real-valued scalar functions on M. So I don't have a metric involved in this step. I'm just thinking about a manifold and all the smooth functions on it. Now, associated with each spacetime Mg is a collection, CMG, which is a subset of S of M. And this collection is the collection of invariant scalar curvature functions constructed from the metric G and its associated Riemann curvature tensor. So the Ricci scalar is in this collection, as well as, infinitely many more. Well, maybe you, if you are a really careful reader, you might look at this constructed from the metric G. And that you might say, well, but what does that mean? What does that mean? There are a number of different ways in which you could perhaps cash that out. What does it mean to be defined by the metric G? Well, under any sense, the Ricci scalar function R has got to count as a member of CMG. I did some poking around in the literature. We could follow the literature, and you might also permit some basic algebraic operations, such that, for example, 108R raised to the -5 halves power counts as a member of CMG when it's defined, right? So this scalar invariant wouldn't be defined on Minkowski spacetime since the Ricci scalar vanishes. Right? So now we're thinking about invariant scalar curvature functions, which they certainly are invariant, they certainly are scalar curvature functions, but they may not be defined on any possible spacetime. Go even a little bit more liberal than that, we're going to permit the use of arbitrary smooth functions so that, for example, alpha of R counts as a member of CMG if alpha is a smooth function. But the important thing to keep in mind in the background is that even under this liberal understanding of metric construction, all the functions in CMG are going to be invariant under isometries. So what do I mean by that? You give me a spacetime and another spacetime, which it's isometric to, and then you take the corresponding functions, which are constructed from the metric in this liberal way, and then you pull back one to the other, they're going to match. That's all I mean by that. So there's an invariance in that sense. Okay, so now my definition. What's the next level of the hierarchy? Well, it's this definition. A spacetime is maximally structured if the collection of all curvature functions, scalar curvature functions, just is the collection of all smooth functions. So you give me an arbitrary smooth function, I don't care where it comes from. As long as it's smooth, then I'm going to do some thing over here, produce a curvature function that matches exactly the smooth function that you gave me. And if I can do that for any smooth function that you give me, then I'm going to say my spacetime is maximally structured. I have a lot to work with. You can see how I have to have a lot to work with if I'm going to do something like that, right? Okay, so any maximally structured spacetime is Heraclitus. This is not a one-liner. This takes a bit to show. Why? Well, the easy way to put it is that there are many levels in between Heraclitus and maximally structured. There's other levels of the hierarchy that I'm not even talking about today. The proof going down each level, it's actually pretty straightforward. It's a little paragraph or something. But when you put 5 of those together, the proof for this takes a page or so. So it shouldn't be immediately evident that this is true, but it is. But I have a question. I really would like the answer to this question. Is every Heraclitus spacetime maximally structured? In other words, are these conditions equivalent conditions? That would be really nice if they were. I've been trying to think of a counterexample, a Heraclitus spacetime which is not maximally structured, but it turns out that the only Heraclitus spacetime that I have around to use and work with is the one that I constructed already and showed you, and it turns out that that one is maximally structured. So that's where I'm going. That's the next proposition, is that I know maximally structured spacetimes exist. Why? Because the one I already showed you is maximally structured. So I want to walk through that just briefly here. So here's a sketch of the proof. Consider the Heraclitus spacetime that I started with tx coordinates. Now use the invariant scalar curvature functions r and f, Euclidean distance to the origin, to define the invariant scalar curvature functions big T and big X, which mimic the coordinate maps little t and little x. So let's get that straight. I mean, these are curvature functions, scalar curvature functions, which are invariant, but they are mimicking the coordinates, which under a usual context, if we're not speaking about maximally structured spacetimes, those coordinates, of course, are not invariant. Okay, and now what we do, so here we see the picture, F and R, and you can kind of see how you could use F and R to form a new coordinate system. F and R really could have been used as a coordinate system here, and that's where the idea is coming from. But once we have this big T and big X scalar curvature invariance, then things tie up nicely. So now you give me any smooth function H. I don't know where it comes from. You just give it to me. And then what I'm going to do is I'm going to construct an invariant scalar curvature function, big H, and I'm going to do it by sending T and X to wherever little h sends big T and big X. And since big T and just is little t and big X just is little x, we find that these functions are the same. And so mg is maximally structured. Okay, so at this highest level of the hierarchy, some even stronger uniqueness results are available. So there are a number of senses in which scalar curvature invariance can be used to determine the local geometry of spacetime. There's some results that are cited. This is a literature that's it's pretty complicated. I don't think any philosophers have taken a look at this stuff. I'd love to better understand these results. But fortunately, we can sidestep that here. I'm going to be focusing on the fact that, in general, even if these invariants determine local geometry, they definitely don't do anything global. So you hear the following, for example, from the folks who do this sort of thing. They don't determine the topology of spacetime. Local invariants can't distinguish a plane and a flat torus. The curvature structure in both of those cases are the same in a sense, and yet they have wildly different global structures. So what I want to do first is make that claim precise. And I'll do that by defining a curvature isomorphism. So let mg and m prime g prime be spacetimes, and let CMG and Cm prime g prime be indexed by a set I to generate their respective families of functions f and f prime. And we do this in such a way that for each little I in big I, fi and fi prime correspond to the same metric construction. So if little I corresponds to the Ricci scalar, well, then this is the Ricci scalar in the one spacetime, and this is the Ricci scalar in the other spacetime. And now what I want to do is I want to say that a bijection from m to m prime is a curvature isomorphism if f prime of I, when you pull it back to m, it just is fi. And that's true for all I. So this definition is supposed to capture a sense in which perhaps the global structure of these models are wildly different. But if there's a curvature isomorphism, then there's some kind of sense in which these spacetimes have the same curvature structure. And so now back to the claim that we found in the literature of plane versus torus. A curvature isomorphism need not be a homeomorphism, let alone a diffeomorphism. So to see that, all you got to do is consider two flat spacetimes with different topologies, and then consider any bijection between those two models. Because there is a local isometry from any point in the one spacetime to any point in the other spacetime, we know that the curvature structure at those 2 points has got to be conserved. And so it doesn't matter what that bijection looks like, the curvature structure will be preserved, and so these spacetimes have the same curvature structure. This is a curvature isomorphism. But of course, we chose our spacetimes to have different topologies, so we know that this bijection cannot be a homeomorphism, let alone a diffeomorphism. Okay, but here's the upshot. If we're willing to go up the hierarchy as high as maximally structured spacetimes, well, a curvature isomorphism between those spacetimes must be a diffeomorphism, and hence a homeomorphism. So this result is exactly analogous to one due to David Malaman in his dissertation, showing that sufficiently rich causal structure determines the topology of spacetime. So recall in that context, what we had is another hierarchy. It wasn't a symmetry or curvature hierarchy, it was a causal hierarchy. And one had, instead of a curvature isomorphism, one had a causal isomorphism. And the claim is that, if you're playing around down here with, spacetimes which are really badly causally behaved, like Gödel spacetime or something, then a causal isomorphism definitely is not a homeomorphism or a diffeomorphism or anything like that. But that as you move up the hierarchy, you get to a level, past and future distinguishing, where if you're working at that level, any causal isomorphism must be a homeomorphism. Even more so, it has to be a diffeomorphism, even a conformal isometry. Okay, so I'm doing exactly the same thing. I have a similar hierarchy that I'm working with. I have a similar kind of isomorphism that I'm working with. I'm after the same kinds of results here. And what I'm saying is that if you give me enough structure, not causal structure, but curvature structure, which is weird enough in the sense that it's highly asymmetric, then I can show that that structure alone will determine the global structure. It'll give me my topology. It'll give me my manifold structure. But I did want to emphasize one important difference. So causal structure of spacetime is encoded in a particular relation between spacetime points. This point is causally related to this one. Scalar curvature structure is not encoded in a relation between spacetime points. We're talking about properties now. So each scalar curvature function gives rise to an invariant property of each spacetime point. And so the scalar curvature structure of spacetime is encoded in the collection of all such properties at all such points. And so what I'm saying is that maximally structured spacetimes have so much structure around that even the properties of spacetime points determine the topology of spacetime. Relations are not needed. So one final way to put this point. You give me a bag of points, a bag of spacetime events. You don't tell me how they're related to each other in any way. You give me no relations between spacetime points at all. All you do is, for each point in the bag, you give me an infinite list of all of its scalar curvature properties. Remember, these are just real numbers associated with each point. So I've got a point and I've got a bunch of real numbers attached onto it. And now put all those points in the bag, mix it around, hand it to me and say, okay, I want you to put together a spacetime. I claim that if I'm working at the maximally structured level, I can only do it in one way. And I don't need any relations to do it. Okay? All right. Conclusion. I'm kind of out of time, right? I'm supposed to end pretty soon.
Well, I mean, we're in question time.
Yeah.
Coffee break will start in 4 minutes.
Okay. Here's the picture again. I could say just a tiny little brief sentence about each one. We started at the bottom. This level captures a sense in which local fixing symmetries in a local region will fix them everywhere. All standard GR spacetimes satisfy this condition, but they can be violated in other spacetime theories. Giraffe spacetimes, this requires that the global structure is already fixed. Everywhere we look in textbooks, we see non-giraffe spacetimes, but we think that these are actually generic among the universes of GR. Heraclitus, now we're fixing the local structure of our symmetries, and at that level, there's a lot of structure around, can prove lots of interesting things. One of the things that we showed was that local structure just kind of is global structure. One can be recovered from the other. And then finally, at the last level, maximally structured spacetimes have even more structure that allow me to recover that global structure if you just give me the properties of spacetime points themselves. So that's where we're at. Thank you very much for listening. Yeah.
We have 3 minutes. I got David, Toby.
Okay, this is a very particular question. I mean, so how much can we, do you know how much we could prove about these things if we were working in linear approximation? Let's say I take Minkowski space-time, I consider a perturbation of it, and I truncate to some low order. My sort of intuition is one ought to be able to prove in that approximation quite a lot of the genericity thing. So that obviously wouldn't constitute proof, but it would be suggestive.
I see. So maybe within that context that they would have much fewer symmetries than you might think about on Minkowski spacetime, and therefore you would be able to prove similar kinds of theorems.
Yeah, and if I ask what my physical intuition here is, it's something like, I take Minkowski spacetime and I just kind of ripple it with gravity wave.
Right.
And I've got enough degrees of freedom as to how I can thus gravity radiation over the generically I'd expect these things to hold.
Yeah, I think I probably share your intuition there. That would be interesting to check out, and probably a little bit easier to get a grip on than maybe some of the problems that I've been looking at.
My thought is that one might well be able to prove a linearized gravity theorem relatively straightforwardly. That wouldn't, turning the other theorem would probably be hideous, but it would be quite heuristically suggestive.
Mm-hmm. Thank you.
Toby?
Just a clarification. What does it amount to for a space-time to be, well, a class of space-time to be generic among classes of space-time?
Yeah, good question. I mean, usually the way folks do it in the early days of GR, one wanted to put a topology on the collection of all possible spacetimes. There turns out to be lots of problems with that, so then they went to this idea where you fix the manifold M, and then you consider all possible metrics on that particular M and put a topology on that. The problem there was that there were a number of different topologies you could use, and none of them seemed entirely satisfactory. And so it's kind of a strange, weird situation. And what makes it more strange is that there was that initial thing that happened in the early days of global structure in 60s, 70s, where we were approaching it in this way. And these days, though, when you hear about, spacetimes being stable in some sense, they have other ideas around that are a little bit more complicated. And so the literature is kind of split in various directions. But generally, I would, for me to understand what's going on, I would definitely like to have at least some class of spacetimes and a nice topology on that class, and then show that if a property is going to be generic, if you give me a spacetime with that property, I'm going to be able to find an open set around that guy with everyone in that open set having the same property. So we have results like that for the causal hierarchy. We have senses in which stable causality is stable in this way. Global hyperbolicity is stable in this way. But it's unclear whether the curvature structure stuff is, or the Heraclitus stuff is amenable to that kind of setup. So I don't know. It's a really good question, and I really want to think more about it when I get some time.
Kenny?
Yeah, so I've a question to see if I understand what's going on and see if it causes a problem for the genericity of the Heraclitean spacetime. So you have this, your giraffe you're working on is this sort of triangle that points to the right. And if we imagine the sort of symmetrized version of that sort of points both to the right and the left, now it's not a giraffe because it has a reflection symmetry, right?
Right.
And then it's also, when you put your thing on it that makes it the original one, Heraclitus, if you put that on this, it's not going to be Heraclitus because every point is going to have exactly one other point that it but then now if we consider anything that's between this 1/2 triangle and this 2/2 triangle, where we put in parts of this spacetime, the parts of the left half, it's not going to be Heraclitus, but it is still going to be a giraffe, right? because some of the points will have their duplicate, but
But not all.
yeah. And I'm just wondering if that sort of construction is going to make you have things that are non-Heraclitus near every Heraclitus thing.
Yeah, I see. So, yeah, the idea is if you, took that triangle and then took the little bit and made it smaller and smaller and smaller, something like that.
Yeah.
Yeah.
So you get things that have arbitrarily small failures of Heracliteanness very close to the Heraclitean.
Yeah, maybe something like that will mess it up. I mean, one thing to keep in mind is that we're going to be working with the standard framework where we're probably going to be fixing the manifold to start. On the other hand, a triangle with a little blood thing, that actually, is diffeomorphic to the triangle. So actually, you do have to worry about situations like that. And so, I don't know. Yeah, good question. You have a follow-up?
So I was just going to say, but couldn't you have it both ways, right? You could have Heraclitus R generic and non-Heraclitus R. I mean, depending how you set things up exactly, it
Yeah,
could be both generic.
that's true too. Yeah,
It's both gangster.
yeah.
Yeah, I mean, your answer to Toby was like about stability results. And I mean, if it's just one density in some topology.
Yeah, thank you. I'll think about that. That seems hard.
Okay, thank you, JB. Let's take 10 minutes for coffee, reconvene at 11:30 for Thomas's talk.
Yeah, he was one of the guys. JB.
Yeah.
I would love to see that. I think of him as kind of my guiding light.
Okay, yeah.